But without further ado, we'll switch over here, and Team Lightning is up first.
Okay. Well, hello everybody. We are Team Lightning. My name is Jacqueline, and
Joey.
I'm Julia.
lots of J's, and we're going to talk to you about the lightning sensor that we built while we were here. So just a quick background, lightning emits in a large range of the electromagnetic frequency, and because of that we can use it to detect lightning. Now there are different ways to detect it. Fast and slow antennas basically measure the vertical change in the electric field, and you can see this diagram on the right. I think this is from Paul Crable. He has a great website with a lot of lightning science on it. And so in lightning, you can see measurements of fast electric field. That's typically what we'll see. This is very fast change in the radiation component of the electric field. It'll look kind of like a heartbeat when you see it. It's a very fast time constant, whereas in the slow field, Joe even talked about that one.
Yeah, with the slow field, essentially you're just continuing to sum up our individual return stroke pulses. So as you can see, as we're having return strokes or lightning channels coming to ground, flashing, we're measuring them in the fast response, but then with the slow response, we're just continuously increasing that voltage.
Yeah, and these are very small time scales. So you can see at the bottom there, like a return stroke, you're getting like a 50 microsecond pulse. But the goal of our project was to build a functioning slow antenna with also a fast channel that we could switch between. And we were going to test by varying different components of it. So we tested the material for shielding. So we have a plastic bowl, and then we have a metal bowl. We also tested how big the plate is, if that affects our signal. So we have, I don't think we brought in this cute little plate. It's so adorable. And then a larger plate to see if that changes our signal. And so, as we said, the materials, we have this nice bowl over here. We have the plastic bowl. We use this for our stopper in the middle. It's ultra high molecular weight plastic, and it was interesting to try to glue to say the least. We tried to insert something into it by melting. That didn't work. We tried super glue. That didn't work. We tried the UV epoxy. That didn't work either. So we ended up having to just screw it into the material itself. But it worked after that. And so Joey's going to talk about the circuit diagram for us.
So essentially, this is our circuitry that we're using to measure the voltage that's coming across the plate. This first side over here is essentially what it is measuring and summing up the charge that's coming across. And also inverts the signal as well across this capacitor. This side of the circuit diagram essentially amplifies that signal as well, so we can get to something that we can actually measure and see within our scales. Again, though, this is an entire analog circuit, so our output is going to have to go to an analog to digital converter so that we can use it with our computer and such. It's something that we went through yesterday. Both the grounds here are not just like technical earth grounds, but they're actually grounded to the bowl. So it's sort of a virtual earth that we're trying to simulate here. Your amplification, though, you can have the gain of the circuit. The gain of the circuit is essentially 1 over the capacitance here. There's also an amplification factor here as well. As you can see, it's a difference of 10. So we have an amplification of 10 here. Also, our time constants is something very important. This is what will determine your fast and your slow side. So essentially, the time constant is R times C, or resistance times the capacitance. So if we have a capacitance of 1 microfarad and a kilo ohm, those units are going to essentially cancel out. That gives us our slow side, or time constant of about 0.1 seconds, I believe, on this one.
Yes, for the slope.
And then obviously with a 100 ohm, you don't have that cancellation factor with a 10 to the negative 6. We're going to have a lot shorter time constant of like
100 microseconds.
100 microseconds, yeah, 0.0001 seconds. Next slide.
And we ran into a lot of interesting issues while we were designing the circuits. We had to learn how to troubleshoot.
There's a lot of troubleshooting, yeah.
Spent a lot of time troubleshooting, which was a learning experience for sure.
Okay, cool. So I'll do the methodology. So we did 4 tests per bowl. So we had the plastic bowl and then that metal bowl. And so we wanted to see how much the plastic bowl would affect the returns, since plastic bowls aren't used at all for slow antennas, and there was some speculation that it would not work at all. And so we wanted to try it out to see if it worked, and we'll go over the results later. But so we did 4 tests per bowl. We did the small plate and the large plate, and for each plate we tested the slow antenna and the fast antenna, so they each had a different measuring time scale. Let's see. So for the slow antenna, we rubbed styrofoam on our heads, and then we counted to 3 and kind of made this motion over the plate to collect the charge.
It's a lot of fun. Trying to get this charge together. Yeah.
Yeah. So we did that for the slow. That was for the slow, and for the fast, we weren't really quick enough to get really solid data. So we used a battery charger, and that battery charger just being there plugged in produced a charge that our fast antenna could pick up. So we had 2 different ways of collecting data for that.
So does anyone want to try this? Okay.
Yeah, we've got short hair and long hair.
Okay.
Is it the movement of the circle down to the plate?
Yeah, you're doing a change, so you have to pull it there in the way, and it's
Yeah.
measuring the charge on the phone. Okay, so we have this ready, so basically just rub it on your head.
Okay, you're charging the styrofoam.
And you can see behind her, this is the voltage, the amplitude of the signal that we're seeing. And once you're ready,
Whenever you're ready.
you can see it showing up on the graph that it's measuring the charge.
So there's our measured charge response on the slow antenna right there.
But yeah, thank you for your volunteering. You're like having a lot of fun. Okay. Thank you. Okay. Okay, going back to the PowerPoint.
So yeah, okay. So for our first test, we did the small plate with the metal bowl. And so with the slow antenna, you've got your maximum amplitude at about 0.08 volts, and you've got a minimum amplitude of about negative 0.05 volts. And for the fast antenna, so this was for the hair, this was for the battery plugged into the wall. You've got much smaller max amplitudes and much larger min amplitudes. But so the max was about at the really large points, it was about 0.05, generally much lower. And for the min, you've got about negative 0.15, which is even larger than your minimum amplitude, or even smaller than your minimum amplitude for your slow antenna. And for the large plate and the metal bowl, so these are both metal bowls. For the slow antenna, we had about a max of about 0.1 volt and a min amplitude of about negative 0.08. These are rough estimates. And for the fast antenna, again, you see the same trend of the much smaller minimum and the lower maximum as well. But about a 0.05 volt max and a negative 0.38 volt.
And then, so moving on to the plastic bowl, we actually saw larger amplitudes in our signals. So this is small plate plastic bowl, and we got up to above 0.1. So the other one was 0.08, if you remember when she was talking. And we still saw the noise source in our fast antenna display with the battery. And then this was actually just Julia rubbing her hands together and testing it, which was interesting. But the one thing we were trying to figure out is if we used a plastic bulb with the static charge build up, and then we had some sort of offset amplitude on there. And from our test, we did not see that happening. It usually would return to 0 each time we did it. And sorry. Moving on to the large plate plastic bowl. Do you want to talk about this one?
Large plate plastic bowl. Essentially now we're starting to see even a larger amplitude on our slow antenna and such. And this could be due to a few reasons. One might just be the plastic, but largely it's because we have a larger collection area, so we just get more charge on that plate. We can also sample it as well. With the fast antenna, we're definitely getting larger magnitudes on some of our data here. And also, this was it's like a baseline that we kind of.
And with this one, you can also see with the slow antenna, like Jackie was saying, some people thought that the plastic would collect the charge and it wouldn't return to zero, but the baseline did return to zero. So, yeah.
And it was just a much larger signal, like I think it was triple the other one.
Yes. Where we're going for 0.1.
We're using the metal bowl, so. But yeah, I mean, this is just a summary of everything that we basically said. So, metal and plastic, they both work. The plastic seems to, for some reason, amplify the charge. And the larger your plate, the larger your signal as well. Yeah.
Any questions, or does anybody else want to come up here and make some signals? And I think that'll be it. That'll be one question.
Yeah, I have a question for you guys.
Yes.
So you know this testing between different plates and different holes, and you had some theories about what the difference between the plastic bowl and metal bowl is. That was wrong. That's okay. But what about the plate? How much bigger of a signal were you expecting when you went for the big plate versus the small plate? And how would you take this instrument and take it to the next level and calibrate it? Right now you have an output of volts, but that's not what you want to measure. Like you want to measure electric fields. How do you convert volts to volts
Per meter. I mean, you would use a distance function of how far away, so knowing where it occurred, the distance that the lightning traveled.
Source, but
Yeah.
all right. Were you guys thinking about it?
No.
I'm not sure. I'm sure what your question is.
Yeah.
Like, are you saying like, were we expecting a larger response with a
We were
larger
expecting
plate?
a larger response, but how much larger of a response?
I mean, we didn't mathematically calculate that.
Why not?
Because, I mean, we were getting a lot of noise too in the signal as well. So, and also that noise wasn't controlled. So you don't know if
I mean,
you're
I'm sure you
around
could
more noisier
calculate it.
signals, so maybe you might be getting a larger amplitude.
Like if you use the surface area of the plate and we could calculate how much charge per surface area it can pick up based on how big you make it. But we didn't do that math, so like I can do it later for you if you'd like.
I want to see if it matches up with the measurements.
Okay, yeah.
So based on what you've learned from your trials and results that you've got, I mean, what are your next steps? What would you do, like, to make changes and adjustments in what you've already done?
Definitely.
And how can you apply this to, on a larger scale?
So one thing we would change, we talked about this already, or we have like with the capacitor. The way that we did the switch right now, we're switching resistors. And if we could actually switch the capacitor, that would have been more helpful with setting our time constant. And that would have made it easier to see the fast channel, because we kind of struggled to pick up anything with the fast channel, unfortunately, with our design. So that's something we would do differently. What do you think?
I think, just like what Jackie was saying, because we're setting the gain with this capacitor, and we were just not getting the amplitude that we would wish, or the responses that we wish with the fast antenna. So that if we could keep this resistance constant and just switch between two capacitors, we'd actually be switching between two gains on the antenna as well. So create one that had a really good response on the slow antenna, but then also one that would also have a really good response that we would like to see on the fast side as well. Something we were seeing.
And if we were going to upscale this and make these like out in the field, obviously we need to do a lot more like weatherproofing, and we'd have to do a lot more testing than we actually did here to make sure that what we're seeing is real and not caused by some sort of noise or we'd have to have a more steady, constant signal to test on versus like our hair. So that's definitely a next step for this if we're going to keep looking at it.
Just a more controlled environment.
Is there any reason like the plate and bowl are the size that they are?
The bowl has to essentially shield the plate.
Sure.
So the bowl is dependent upon the plate size. And the plate size is going to be kind of sensitive to how you want your measurements. If you had trigger lightning, like you were triggering lightning off a rocket right outside, you wouldn't want a large plate. because you're just gonna oversaturate. So a smaller plate would be better. If you wanted something that was more wide-ranging, you'd want a larger plate to hopefully capture those smaller signals. The bowl in this here essentially just acts as a shield for precipitation, so that you're not getting charged precipitation on the plate, and it's driving the signal off.
How far away do you think you can measure lightning?
Depends on if it's a fast or slowing channel. So, well, do you want to, or I can. So basically, if we're looking at the slow channel, typically you can see very close, so you're only going to see it out to like maybe 15 kilometers. You want to be really close to the signal. Whereas our fast channel can see very far away because it's looking at a different part of the spectrum, and due to that, it's looking at radiation changes, which are 1 over R, so the drop-off is a lot slower than your 1 over R cubed electrostatic change. So you can see lightning in the radiation field like hundreds of kilometers away, or further, depending on how you have your circuit set up and all of your resistance and capacitance for your time constant.
What do you have?